morning. I am Renu Sharma, Assistant Professor EC Department. The topic of today's lecture is channel modeling, part 2. In the previous lecture, we have discussed about the channel modeling, how we have to model a channel. In this, we are going to discuss what are the exactly models that are designed. First is the wireless channel modeling, then AWGN, and then Okumura and Hotta model, that is one of the outdoor channel model that exist. Now, this is the introduction of wireless channel modeling. So, perfect channel modeling is required to study or analyze a wireless system. A channel can be modeled by two approaches, that is physical and statistical. So, physical and statistical two are the approaches that we have to see for modeling a channel. In case of physical, we have to see multiple hops, like I am talking from the 2-3 lectures about. It may be possible that there will be a hill exist between the transmitter and receiver, a building will be there. So, these are the physical objects. So, that undergoes when the signal that will going to impinge on these particular objects, that will undergo reflection, refraction, scattering, diffraction. So, that are the parameters for you have to consider for the physical modeling of a channel. When we are talking about the statistical model, in that we have to consider different distributions, probability density functions of Rayleigh channel model, of Rayleigh model, of Rayleigh distribution, of region model. Then in case of Okumura and Hotta model, there are different formulas that we are going to discuss in this lecture. So, it is based on the statistical analysis, where different input signals are applied, because input will going to change every time, and the characteristics and the channel modeling will be same, the model of the channel will be same, and it will be seen at the receiver side, that what will be the statistical received signal that we have calculated after passing through a particular distribution. So, reflection, multipath attenuation and are considered for the physical approach, and input and output elements and transaction probabilities are considered in the statistical approach. So, important properties are like channel may be time varying or it will be static in nature. The effect of mobility is that the channel varies with the user's location and time. Since this is mobile communication, two things are there. First is it is wireless. Secondly, mobile. Mobile means it is not your handset, it is when the transmitter and receiver, it will be possible that both are moving in nature, but most of the time the receiver to which you are initiating a call is moving in nature. So, when it is moving in nature, then Doppler shift or Doppler effect comes into the picture, that will going to change the characteristics of the signal. So, depending on the user's location, which means at time t naught the user will be present here, like at t naught the user will be present here, t 1 the user will be present here, t 2 the user will be present here. So, whatever signal is received here, here and here, it will be changed in time. So, it will be time varying or it can be static in nature. Static is only possible when the receiver is moving at a very small, very less speed, and it will be static in nature. So, the slower one moves, the lesser variation will be there, which means when the receiver is moving at a very slow speed, then the signal which is received at the receiver side, it has very less variation as compared to when the receiver is moving at a very fast speed. Channels may be time dispersive or non-dispersive in nature. Due to the dispersion, the pulse spreading will be observed which will result in intersymbol interference. So, channel will be dispersive or non-dispersive, which means that whenever the signal which will travel over the channel, like this is the signal which is travel over the channel, this is channel, then it gets spread. This is known as the spreading of the pulse. This spreading is due to the intersymbol interference, that is known as ISI. Intersymbol interference means this will be changed, it will undergo the intersymbol interference concept, which means the mixing of the pulses from the neighboring user is there. So, that is known as ISI. Now, next is channel may be linear or non-linear in nature. So, all the channels act as a low pass filter under under certain conditions as they show, the pulse spreading effect will be there. Now, channels may be fast or slow fading and may be frequency selective or flat fading. So, fast and slow fading means it depends on the speed of the receiver it is moving at. If it is moving at a very fast speed, that is known as fast fading. If it is moving at a very slow speed, then that is known as slow fading. It can be a frequency selective fading, it can be a flat fading. So, 4 types of fading are also there, that comes under small scale fading. Now, next is the channel modeling and probability theory. So, the following are the few definitions that are useful for understanding the statistical way of channel modeling. Like first one is the probability density function PDF. PDF is a very important parameter for designing a channel model, and it is specified for probability density function. It will be specified for Rayleigh channel, there will be different PDF, region channel has their own PDF, Gaussian function has their own PDFs, that is fixed in nature. You have to just apply the input which is variable. Every time you are applying, it is not possible that the same input will be there, but the channel will be same, it has fixed PDF, then the output can be calculated. So, it describes the probability that a real valued random variable in m will be found at value m. In other words, it describes the relative likelihood for this random variable to take on a given value. Now, PDF is non-negative everywhere. So, it is the integral over the entire space which is equal to 1. So, that is, which means for the PDF the important property is that minus infinity to infinity f x dx will be is equals to 1, which is written over here. PDF is non-negative everywhere, it will be positive and it has positive values, and its integral over the entire space, which means from minus infinity to infinity it is equals to 1. Now, there is a relation between PDF and CDF. CDF is the cumulative distribution function. It describes the probability that a real valued random variable m with a given probability distribution will be found at the value less than or equal to m. So, it is the area under the probability distribution. CDF is the integration of the PDF, which means CDF is the integration of the PDF, or reverse is also true, PDF is the differentiation of CDF. Then Gaussian process. Gaussian process, it is a stochastic process and its realization consists of random values associated with every sample point of the space, such that the random variable has a normal distribution. So, that is Gaussian process. So, 3 things you have to keep in mind while designing a channel using probability theory. First one is PDF, that is specified to every distribution. Then CDF is related to PDF, that is in terms of integration and differentiation. And third thing is the Gaussian process, because the Gaussian process, why we consider, because this transformation and inverse transformation is same when we consider for a particular Gaussian distribution. Now, next is correlation of fading and auto covariance. So, these are some of the parameters that you have heard earlier, which has to be considered while designing the channel. So, if the process is formed from a sequence of Gaussian random variables, that is denoted by x n, and if they are uncorrelated to each other, then the process is known as white Gaussian noise. So, white Gaussian noise, Johnson noise, thermal noise are all same in having different name, but all are same. Its process is defined from a sequence of Gaussian random variables which are uncorrelated to each other, then it is white Gaussian noise. For each x n, we can find the mean and variance. 2 other ensemble averages are autocovariance and autocorrelation. These are calculated as mean. Now, mean will be is equals to m x n, which is equals to expected value of x n. Now, x n is nothing, it is the random variable. If we are going to calculate its mean value, then that is denoted by m x n, or it can also be written as mu. Next is the variance. Now, variance is nothing, it is sigma x square, which is equals to expected value of x n minus mu whole square. Now, mu is nothing, it is the mean. So, expected value of this random variable x n minus mu whole square is known as the variance. Next one is auto covariance. Now, auto covariance is expected value of x k minus m x k n and x l minus m x l. So, that is the auto covariance. Auto correlation is denoted by this r x k comma l, that is expected value of x k convolution with x l. So, this is how you have to calculate the autocorrelation. Now, autocorrelation is having value minus 1, 0 or 1, means if two random variables are correlated to each other, strongly correlated, then its correlation coefficient is equals to 1, that is denoted by rho. If it is totally uncorrelated, then its correlation coefficient will be equals to 0, and if it is related, but it is opposite in nature, so then its value correlation coefficient will be equals to minus 1. So, these three parameters you have to keep in mind for correlation. Next, we will move to AWGN. AWGN is nothing, it is additive white Gaussian noise. Why it is additive? Because this noise is additive in nature. You can add to the input signal for the mathematical analysis. It is white Gaussian noise, means it is based on the Gaussian distributions whose PDF is written over here, that is universal. P x will be equals to 1 upon under root 2 pi sigma square e to the power minus x minus m whole square upon 2 sigma square. Now, m is nothing, it is the mean, sigma square is nothing, it is the variance of this particular variable, that is x. Now, the noise is additive in nature. The received signal equals the transmit signal plus the noise. So, when the noise is statistically independent of the signal, which means that this is, let us say this is x t, and this will be added together with the noise, and this will be the received signal. So, you can write directly R t will be equals to x t plus n t. This is only possible when noise is uncorrelated with x t, because it will not going to affect, means this is not added or multiplied together. If it is correlated, you have to perform multiplication in time domain and convolution in frequency domain, but if it is independent in nature, then you can directly add it together to calculate the received signal. Now, the noise is white, which means it has a constant PST, that is power spectral density, which is constant, means from minus infinity to infinity its value is n naught by 2. The autocorrelation of the noise in time domain is 0 for any non-zero time offset. The one sided PST is usually n naught and two sided is n naught by 2, means I am considering this two sided, then this is n naught by 2. If it is one sided to up to infinity, it will be n naught, that is the power spectral density. So, that is why it is white, known as white, additive white Gaussian noise. Now, the noise sample have Gaussian distribution. So, the Gaussian PDF is given by having variance sigma square and mu mean mu. So, P x will be equals to 1 upon under root 2 pi sigma square e to the power minus x minus m whole square upon 2 sigma square. So, that is the additive white Gaussian noise. Now, this is the representation of the discrete channel by filter. So, conceptually, if an impulse is transmitted on a stationary channel, then at a receiver the multiple delayed version of impulses will be received at different instant of time due to multipath, which means the channel is static in nature, it is stationary in channel, the channel is not moving, but due to multiple hops the channel will be impinged on different objects, then there will be delayed version of that particular signal will be there of the impulse function, then these all will be added together due to multipath. So, these impulses are not correlated to each other and with reducing amplitudes with time. So, they are just like the delayed samples, and hence a difference equation with coefficient values can be used to represent this concept. So, which is the equation for a finite impulse response, that is denoted by FIR filter. So, that can be written as R n, that is the received signal will be equals to W naught n into S n plus W 1 S n minus 1 plus W 2 S n minus 2 up to so on. So, these are the weight functions, these are the received signals that has value S n, S n minus 1, S n minus 2, S n minus 3 and so on. Then the channel model for a time varying channel can be approximated by a auto regressive channel model, that is denoted by H n plus 1 is equals to W 1 H n plus W 2 H n minus 1 plus W n H n minus n plus W n. So, this is nothing, this is just the noise which is been calculated after passing through a channel, and these are the weighted functions that we have multiplied with the signal. So, where W's are the weights and the coefficients to estimate the particular channel. So, this is the representation of the discrete channel by filter. Now, next is the Okumura model. Now, Okumura model is nothing, it is an outdoor model that is based on the various distribution functions that we have seen over here. It has its own formula, it has various parameters like frequency, transmitter height, receiver height, distance between the transmitter and receiver, and depending on this you can see that 3 types of prediction areas were considered in Okumura model, and these 3 areas are, first one is open area, suburban area and urban areas. So, how these areas are characterized? Depending on the population, number of intermediate nodes, number of hops that exist between the transmitter and receiver, the areas are designed, the areas are decided. Like first one is the open area. Now, open spaces with no tall trees or buildings in path are there. So, that is known as open area. Suburban areas are village highways scattered with trees and houses and some obstacles near the mobile, but not very congested. So, that is known as the suburban area. Urban area is built up cities or large towns with large building and houses and villages with close houses and tall trees, which means very congested area comes under urban areas, whether we are talking in terms of population, houses which are congested. So, there will be very large number of hops exist between the transmitter and receiver. In case of suburban areas, the village highways scattered with trees and houses and some obstacles near the mobile, but it is not very congested as compared to the urban areas. And open areas is nothing, it is field region, rice field region, the farming lands, that comes under the open area where population is very small, very less population is there. So, the Okumura model considers several parameters. The output parameters is the mean path loss or median path loss, which is denoted in decibels, for which the calculations are made as follows. Like this is the frequency f c between 150 megahertz to 1920 megahertz, typically extrapolated up to 3000 megahertz. So, this is the range of frequency that we can consider. Next is the transmitter height, that is denoted by h t, which exists between 30 meter and 1000 meter. Next is the receiver height, that is h r, which exists between 1 meter to 10 meter. Then between the transmitter and receiver distance, it will be denoted, the transmitter receiver distance is denoted between 1 and 100 kilometer. So, this is the consideration that we have 4 parameters, that is f c, then there will be h t, there will be h r and there will be d. These 4 parameters we have seen. This is the frequency range, this is transmitter height, this is receiver height, and distance between the transmitter and receiver denoted by small d. This is the Okumura model. Now, Okumura model is loss is denoted by this L in dB, which is equals to L f s 1, that is the first frequency in decibel. This is ADM, that is the mean attenuation. Then HMG, that is the mobile station antenna height gain factor. HBG is base station antenna height gain factor. K correction is the correction factor gain, such as type of environment, water surfaces and isolated objects. So, all these things have to be added together for calculating this correction factor. This has to be subtracted, because when we are calculating the value of L, that is path loss, then all these correction factors have to be subtracted, because we are calculating the loss only in decibel. HM is the mobile station antenna height above the local terrain height in meters. D is the distance between the mobile and building in meters. H naught is nothing, it is the height of a building or object above the local terrain height in meters. HB is the base station antenna height. R is the great circle distance between base station and mobile in meters. D is denoted by R into 10 to the power minus 3, that is great circle distance between the base station and mobile in kilometers. F is the carrier frequency in hertz, Fc is the carrier frequency in megahertz. Lambda is free space wavelength in meters. So, this is how this Okumura model is designed. This is loss in decibel, this is HM, DM, height and distance, these are the different parameters. Now, Okumura model is extended by Hata. So, it is known as Okumura Hata model. In this model also there are parameters like frequency, that is denoted by 150 ranges from 150 megahertz to 1500 megahertz. Its transmitter base station is height is 30 meter to 200 meter, then receiver height is 1 meter to 10 meter, transmitter receiver distance exists between 1 meter to 20 kilometer. So, for different areas you can see, like for the open areas its value is L loss in decibel is equals to A plus B log to the base 10 D minus capital D. For the suburban areas it is A plus B log to the base 10 D minus C. For the urban areas it is A plus B log to the base 10 D minus E. So, you can see in the three formulas this C, D, E will going to change and the first two terms are same. So, what do you mean after seeing this formula you are imagining, so what are the values are A, B, C, D and E. So, this is written in this next slide, that you have to, if you want to solve that formula, because those three formulas are very simple, but if you want to calculate the A, B, C, D, E parameters, where E is different, again different for the different in terms of population. So, for large cities it is Fc is greater than equals to 300 megahertz, for large cities it is less than 300 megahertz, for medium and small cities the values will be this one. So, in this case the A parameter is calculated by 69.5 plus this one, where Fc will be there plus Hb. Now, Hb is the height of the base station antenna. Now, B parameter will be calculated by using this Hb, that is the height of the base station antenna again. Fc is the frequency range that you are using, Hm is the height of the mobile. So, in this you can see that Hb is the transmitter, Hm is the receiver. Not always, it may be possible that we are considering the reverse channel also. So, that will be, this will be the transmitter, this will be the receiver and Fc. So, these four terms you have to keep in mind while designing this Okumura model. So, this is only one of the model that I had discussed in this lecture, but there are different models are there, like Nakagami model is there, that is also again an outdoor model, and I have not discussed the indoor models, which is based on different probability distributions like Rayleigh distribution, region distribution. So, these these models also exist, which I am going to discuss in the coming lectures. So, let me summarize about today's lecture, that is wireless channel modeling. Wireless channel modeling, I have discussed about how the channel has to be modeled. It is modeled on the basis of two approaches. First one is physical one, second is statistical. In physical, we have to consider different parameters for the multipath propagation, like the reflection, diffraction, scattering, and in case of statistical we have to find out the various we have to consider various multiple hops are there which exist and various distribution functions are there which we have to consider while designing a channel. Then some parameters are there, properties like it can be time varying, it can be time dispersive or not, it can be linear, it can be flat fading, different fadings are there. Then we have seen different three important terms, that is probability density function, cumulative distribution function and Gaussian process. PDF and CDF are both related to each other in terms of integration and differentiation, and then Gaussian process we have seen. Then these are some of the important terms, that is mean, variance, autocovariance and autocorrelation, where we have also seen the correlation coefficient. Then AWG and noise, which has its own Gaussian distribution function, which constitutes mean and variance. Then channel model is there, then Okumura model, which is divided in three different areas: open areas, urban areas and suburban areas. So, that is Okumura model. Then it is extended by Hata. So, that is known as Hata model. These are the equations for Okumura and Hata model. Now, these are the references that you can consider for this particular topic. Thank you.